click on this. Organization chem study, and the focal point is, of course, to build the fundamental particles through the more complex structures and then put them together to see how it applies to the study of matter. And subtitle to this is Atoms, Molecules, and Ions. And this, now in the introductory lecture on this, we said chemistry is the study of matter. Anything that has weight and occupies space. And then I took you through a breakdown of matter into mixtures and substances and down to atoms and molecules and so forth. Well, the organization of the study, chem study, does the same thing. It breaks down to the simplest forms of matter, and then we study that and put it together and build it back up to the more complex. And the one issue that is the foundation for the chem study and study of matter is what we call Dalton's atomic theory. And the postulates of this are, you can find them online easy enough, but they start out with all matter is made up of particles called atoms. Well, we know they're more fundamental particles today. And then he builds up atoms interact and form molecules and reactions and so forth. But from Dalton's atomic theory, I paraphrase it in the following way. When we study the course in chemistry, we're going to start with fundamental particles. Of course, the protons, neutrons, and of course the electrons, and then put those together into atoms. See what the structure of the atom is, and a little bit of history on how to describe the atom and so forth, and elements. And this, of course, leads to the periodic table. And then atoms interact with other atoms or elements and form molecules. And compounds. And out of that issue of compounds, we classify the types of compounds in two forms. Ionic compounds, and I'll abbreviate compounds, and molecular compounds. Putting together cations and anions of positive fragments and negative fragments to hook up to form more complex systems of molecules. Now, molecules and atoms interact by a process of chemical reactions. And then you will, once we get through those, this is pretty much chapter 2, and then we'll have a chapter exclusively on chemical reactions. And the types of reactions are really two forms, oxidation reduction and what we call a metathesis. Oxidation reductions do not change oxidation states. No, oxidation reductions do change oxidation states between elements on the reactant product side, but the metathesis do not, and then distinguishes the two basic ideas of those chemical reactions. Now, out of a chemical reaction, you only get three things. Anybody know what those are? No, three things: solid, a liquid, and a gas. Now, there are a lot of forms, okay? And so, after a thorough study of chemical reactions, we'll look at states of matter, really. Solids, liquids, and of course gases. And the last kind of part in this brief outline of chem study is the study of solutions. This is, of course, the mixture of two states in which you take a solid and dissolve it in a liquid, or have gases, and so the complexity of solutions is kind of the top of the pyramid in the study of matter. In your outline, it has a topic that I have moved to after the periodic table. Atomic theory, well, the law of definite proportions deals mostly with compounds. So what I'm going to do is start with atomic structure in here. And talk to you a little bit about the description of atoms and a little bit about the history, and we'll repeat this in down the road, and I think it's chapter 7, I believe it is. Atomic structure refers to models of the atom. What does the atom look like? And nobody's seen one hands-on, so our evidence of what an atom looks like is based upon indirect evidence. It sends us signals that we interpret as to what its structure is. Well, over the years, there have evolved 4 atomic models. This is your historical cross-section. The Thomson plum pudding model was the first one proposed. Rutherford shell model the Bohr concentric ring model, and the one we subscribe to today is called the Schrodinger quantum model. Just a brief cross-section of each one of these. The Thomson plum pudding model was proposed as a spherical positive field with embedded electrons. At the time this gentleman proposed the structure of the atom, they knew about opposite charges, positive and negatives. And so he proposed that the atom, based on his observations, and I'm not going into those details, but he proposed that the atom is a spherical positive field. In 3 dimensions. And within that positive field were embedded suspended electrons. You can see these. Suspended in that environment, like plums in a gelatin pudding. That's where it came from, the idea of the plum pudding model. Well, that didn't last very long, because the second model, the Rutherford shell model, was based upon an experiment to prove the Thomson plum pudding model. That was his objective. And what he did is he set up a alpha particle generator and put a sample of heavy metal into a lead block. And so it would direct the alpha particles at a thin film of gold foil that was inside a photo chamber. That says photo chamber, believe it or not. Maybe that's a little better. Well, the theory was that if this is a positive field and an alpha particle is nothing more than a helium nucleus with a +2 charge on it. So he's firing these +2 charges like a machine gun at this gold foil. His expectation is like charges will repel one another. So he was expecting everything to be repelled. But what he observed was 99.99+% of the particles proceeded straight through and didn't reflect from anything. A very small percentage were reflected off at a very, very small, an obtuse angle, as he said, and then there were some that were reflected right back at the source. And so, through the math and all the other stuff that goes with this, he came up with the conclusion that the atom is mostly space. It was not a spherical issue like this. It was a structure that consisted of spherical electron clouds, and in the center of the cloud, the electron clouds, was a dense, indivisible, he didn't know about splitting the atom and so forth, and it was in the center of this field of electrons. And based on his evidence, the alpha particles, for the most part, just passed right on through, and if one came very close, was reflected at an obtuse, and if one might hit directly to the nucleus, it would be reflected straight back. So his ultimate proposal in his theory is that the atom consists of two parts: a dense, indivisible core called the nucleus, surrounded by a diffuse electron cloud. This up. And so in his proposal and papers, a spherical electronic cloud and a nucleus. Of electrons, as you would expect, and then a dense, indivisible nucleus, positive nucleus, I should say. So that was the second model. The first one was the Thomson, now the Rutherford model. He won the Nobel Prize for this theory. Some of the issues did not come together in terms of the observations and the math and what have you. And we will look at that in greater detail when we get into the chapters on atomic theory. Right now, I just want to give you the cross-section of what each model is involved. So a gentleman named Niels Bohr developed the next theory of the atomic structure. Now, this structure was based upon what we call atomic spectrum. And what this means is a quantity of gas is confined in what we call a discharge tube. I've got one, I should have brought it out, but we'll see it eventually. And the tube is connected to a transformer, electrical transformer, negative charge, positive charge. Short side of the symbology is always the negative. But in here, there is hydrogen gas in that tube, and when circuit's closed, this will have a lavender glow to it. And I'll just use kind of a reddish color for right now, and I'll try to get that discharge tube during the break. Well, if this color is observed through a prism, it breaks up into what we call bright line spectra. And same thing happens in, say, running white light through a prism where you see the rainbow. That's called the continuous spectrum. But if you have a pure element like hydrogen, what will happen is it'll break up into 4 colors. Actually 5, but you can't see the high end of this. Let me draw. Say if you had a screen where you could project this spectrum, what you would see is a red line, a green line, a blue line, and a purple line. About like that, and these were measured to be at certain wavelengths. I believe this one, lambda, is the symbology for a wavelength, 656 nanometers, and I'm trying to prove a point, of course, 486 nanometers. Blue one was 410 and 396 nanometers. Okay, now the point I'm trying to make here is that these are referred to as discrete wavelengths. What do I mean by discrete wavelengths? Long story short, this band of color, red line, is 656 nanometer wavelength. That's a wave, okay, a sine wave. It's not 656.1, it's not 656.3, it's not 655.9. It is one specific wavelength. That's why they call it a discrete wavelength. Well, what does that mean in terms of atomic structure? It means that the electron, when it falls from a high orbital to a low orbital, gives off energy, much like, watch, if I take this pen and drop it, I think everybody agrees that it loses kind of mechanical energy, right? I mean, going from a high position down to my hand, what happens? It loses energy. It's got positional energy in one spot, and then you drop it, it's got a lower energy. Well, electrons do the same thing. And so what the proposal was, if the nucleus is here and you have let me move my sine wave, say those are fragments of rings, and call them energy levels. Actually, there's 7, 4, 5, 6, and 7. It's logarithmic nature. Not to worry with, not important at the moment. And that's ring 7. Well, ground state is a term you need to, at this point, learn. Hydrogen, first one on the periodic table, has 1 proton, 1 electron. And most of you would draw it like that. There you go. There's hydrogen. Got a proton in the middle and an electron whirling around out there. In the first energy level, when all the electrons of a given atom are in the lowest available energy level, is called the ground state of that atom. Make sense to you? That's what we're referring to. However, electrons can absorb light energy. It's like kicking a football. Okay, so it's called electromagnetic radiation is absorbed by the electron. And if you start here, then it has the ability to jump out to higher levels. And consider a tube full of billions of atoms. And then all the electrons, or all billion of them, going out. Some of them will go to the second level. Some of them will go to the third level. Some of them will go to the fourth, fifth, sixth, and on up to the 7th level. And then they'll fall back toward the ground state. Like rocks, dropping rocks off a cliff. Okay? That makes sense to you? Well, what happened? Well, we'll talk about transitions that end on 2. That's the visible spectrum. When an electron jumps out to 3 and falls back to 2, or an electron jumps out to 4 and falls back from 4 to 2, 5 to 2, and get messy, 6 to 2. You can't see the 7 to 2 transition, too high of an energy. But the length of these arrows I'm drawing represent steadily increasing energy from left to right. And it turns out that a transition from 3 to 2 is the red line. The smallest one, that's the lowest energy. Transition from 4 to 2 is the green line, and the transition from 5 to 2 is I find it, yeah. The blue line, and a purple line is, of course, the 6 to 2, and ultraviolet goes, which you can't see, is even what we call UV, ultraviolet levels. Well, what this leads to is that the electron, and this is where you may have heard of the phrase quantum leap. Okay? And what they found was that the electron is either in number 3 or in the ground state, or number 2, or drops to 1. But nowhere in between those lines, those circles. So if you have an element, you might have an electron here, and then it moves to there. But there's no pause between those rings. None. If it were, you would have a continuous spectrum. because this is a discrete energy transition, a specific distance. And as they propose that, well, the electron exists at specific distances from the nucleus, then it must orbit the nucleus much like the planets orbit the sun. And so they came up, I say they, Bohr's group, came up with the nucleus and the concentric ring model. And that's where that's the origin. But I want you to kind of understand some of the foundations that led to this. And that now you have a nucleus and a structured electronic cloud. And the elements, the electrons are placed strategically in those rings, even though they can absorb energy and lose energy and move back and forth within the cloud. The ground state is what is being defined as the concentric ring model. And hydrogen has one, then you have two for helium, and then you have lithium, beryllium, boron, carbon, and so you progressively add electrons from hydrogen up. And those all electrons are bouncing around, and every element has its own spectrum, bright line spectrum, and it's like a fingerprint. And so this is the language that's used to identify, say, what elements make up the sun. Why does the sun energy do what it's doing? Well, when they observe it, they look at a spectra of it, they see this spectrum indicating that as a hydrogen fusion type reaction. But anyway, that's the Bohr model synopsis. So the fourth model of the atom, and the one we subscribe to today in great detail. Now, understand that a theory, no theory is better than the other ones. What you do as a scientist is pick the theory that best fits the problem you're working on. And that's the best theory at the time. So in essence, the one that fits the data best is the quantum model of the atom. And it's based upon what we call the wave-particle duality of matter, of the electron. This simply means that the electron can behave both as a material object, a particle, as well as a wave function. It has both properties at the same time. Well, evidence and study of atoms and spectra lead to evidence that suggests a dual behavior. And essentially what the wave-particle duality of the electron leads to is a field of study known as quantum mechanics. And this is the study of the character of the electron in terms of its energy properties. That's good enough for right now. We'll detail it a little more when we get over into the chapter on this. Well, to describe the electron character or the behavior of the electron in terms of quantum characteristics or quantum mechanics, it leads to what we call quantum numbers. each electron has its own private set of 4 quantum numbers. And IQNs, quantum numbers. They're called principal, orbital, magnetic, and spin. Symbology is as follows. So when an electron is defined, it is defined in terms of these 4 quantum numbers, N, L, M, and M sub s. Now, assigning numbers to this is something we will reserve until the chapter on atomic structure and how to deal with that. But what I want you to understand about this set of numbers is that, like I mentioned a second ago, no 2 electrons have the same set of 4. Well, why is that important? This means that they don't run into each other. This is what I refer to as the electrons singular and electrons energy window. Which means that when you consider uranium number 92, it has 92 electrons buzzing around at its light speed, but they don't run into each other because each electron in that electronic structure has its own private set of 4 quantum numbers, and nobody else can occupy his energy window or house or however you want to count it. So that's the simplest format that I can give you. Now, application of this has led to what we call electron configurations of the atom. Some of you have seen 1s2, 2s2, 2p6, 3s2, 3p6, and so forth. And it evolves, and each one of those sets of symbols defines the electronic structure of the atom. Now, that's as far as I'm going to go with this in terms of giving you a historical cross-section. So what I'm trying to do is set the stage for building from the most fundamental structures of atoms through the more complex solutions and solution properties that we will see as we have advanced through the textbooks. So please spend some time learning the little history here. There's nothing complex in there, it's mostly factoids, but I do want you to be aware of the historical cross-section, the Thomson plum pudding model. Some people will call it the raisin pudding model, same idea. Suspending some fruit in a gel pudding. Rutherford shell model. Oh, one footnote on the Rutherford. He was the first, please jot this down, the first to propose the 2-part atom. Rutherford was the first to propose 2-part atom. Test question, hint, hint. And so, hang tough, guys. Anyway, then the concentric ring model, many of us, the chemical community, still use the concentric ring model. It's just very convenient in defining reactions and what have you, especially the outer shell structures. You know, all chemistry takes place at the valence level. The core structure of the atom, which we are going to look at in a minute, is inert, so to speak. It's not reactive. Well, there are always exceptions, but anyway. Then, of course, the quantum model, which is our modern defined structure of the atom, and we will develop that in more detail as we get to those chapters. Again, Rutherford was the first to propose a 2-part atomic structure. The nucleus having a positive charge and the electron cloud. And the Bohr model shows 7 rings around it. The reason we have 7 rings, listen to me, there's 7 rows on the periodic chart. Okay, you can have more than 7 rings, but we only know of 7. All right. The nucleus is composed of protons and neutrons for the most part. One element does not have any neutrons. Anybody know what that one is? Hydrogen. Right. But all the others have neutrons, including hydrogen has isotopes, and we'll talk about those eventually in variations of the nucleus here in a few minutes. But the nucleus consisting of protons and neutrons, and then of course the rings make up the electronic cloud. And as it is structured, it is divided into energy levels based upon the concentric ring model. The first energy level is given n equal 1. Second energy level is said to be n equal 2. Actually, these are called principal quantum numbers, location of the electrons. N equal 3, n equal 4, 5, 6, 7. And so electrons are placed in each one of these sequentially until you build up to whatever element you are interested in studying. And that's called the building up process, and that will be an important little phrase as we get into writing electron configurations, the 1s2, 2s2 stuff later on. And now, one little footnote in here, and it's very easy to calculate the maximum number of electrons in a given electronic orbital is equal to 2n squared, where n is the ring number, or principal quantum number. So if now remember 2n squared, because I'll ask you on the quiz, what's the maximum number of electrons you can put in the second energy level? Okay? Well, the first energy level, you substitute 1, you can put 2 electrons in there. No. And, all right, if you put 2 in where n is, 2 times 2 is 4, so you can max out at 8 electrons there. 8. 9, 2 to 9 is 18, and then 1632, 50, 72, and 49, 98, yeah. Now, it doesn't mean that they have to have that many. It's just room for that many electrons. And the placement of electrons about the nucleus for a given element follows certain rules of the building up process as we build up the atom of interest. Now, the organization of the periodic table begins with what we call the element block. So each element has its own personal element block. And so as you look at this, you see a little square for hydrogen, and then it goes over, of course, to helium and lithium and so forth. Now, on this chart, and this will be one that will be attached to your exam when you take your exam. It contains 3 primary data issues that you need. Of course, the symbol, and then you have a proton number or atomic number and an atomic mass. So for any of the elements, 3 data points are listed, have to be listed. So you have the symbol, and then you have, say, the atomic number, and it's listed in the literature as a zebra number. And then you have A, the atomic mass. In such, the atomic mass is the sum of the number of protons and neutrons. But the atomic number is always equal to the number of protons in the nucleus. Now, in writing the symbology for elements, there are a couple of ways to do it. X, and it's all, listen to me, big number over little number. Okay, so A is always the larger number except for hydrogen. And so the mass A will always go over Z. And if you take A minus Z, you get the number of neutrons. For example, if we take oxygen, a mass 16 rounded off, and 8, like that, it has 8 protons, but how many neutrons does it have? Well, we take big number minus little number, and we get 8 neutrons. So there's 8 neutrons in the nucleus. If we're talking about just neutral elements, then the number of electrons always equals the number of protons. Like that. There's one more here. Uranium has an atomic number 92, like that. And the most abundant isotope of uranium is 238, uranium-238. Well, looking at this, we have 92 protons, and then 238 minus 92 is 146 neutrons. Now, since it's, say, we're working with a neutral uranium, it's 92 electrons. So it's a pretty straightforward little calculation in terms of determining how many neutrons, protons, and electrons are associated with a given atom. Placement of the electrons is another story, and we'll cover that in due time. So, writing the elements. Now that's just, you don't have to put a negative in there, just 16 over 8. Just take any one, let's take silicon, number 14. And it has an isotope of 28. Like that. Well, silicon may have several isotopes, okay, which means they have different atomic masses. So you might have a silicon 28 and a silicon 29 and a silicon 30, like that. But the one thing they all have is the same atomic number, or the number of protons, but they have different atomic masses. So a second symbology method is frequently used in writing elements and isotopes. So now since they all will have the same atomic number, that defines the element. Then you can find literature, if they're using this, Si-28 or Si-29 or Si silicon 30. So all that is listed after the element is the atomic mass, rounded to the nearest whole number. And if we're looking at the uranium, like U-238, you might find it written in the literature like this, and U-235. That's fissionable uranium. So those are symbology things that you need to be aware of as we go forward in the material and how to define these elements. When we talk about variations in atomic structure, we're talking about nuclear variations and electronic variations. Nuclear variations lead us to a topic known as isotopes, whereas the electronic variations lead us to a topic known as ions, charged particles. Beginning with nuclear variations and isotopes, isotopes, by definition, is a set of elements all having the same atomic number but different atomic masses. Because of neutrons, of the number of neutrons. There we go. Like one here is isotope, and it's identified as X63 and X65. They give you isotopic masses and fractional abundance. What's the weight average atomic mass of the element? Well, the handout that I gave you is one for oxygen. And what I want you to notice first here in this, I'll move it back, is when we calculate this, none of the isotopic masses that will be given will match those on the periodic table. Oh, here. Did y'all get... Okay. Write these into your chart. The isotopic mass for oxygen 16 is 15.9949. The isotopic mass for oxygen 17 is 16.9991. '18 is 17.9992. like this. So you'll be given a problem with the either in a percent abundance like this one, or in a fractional abundance format like that one. Well, note on here the isotopic masses do not match the mass of oxygen on the periodic table. So if you look at the value for the periodic table here is 15.999. Actually, the one on the chart up there is 9994. So what's the deal in this? The number on the periodic table is called a weighted average of all the isotopes. And the weighted average of these isotopes is what goes on the periodic table. That should be an A there, make it look a little more like an A. It's the fractional sum of the fractional abundance times the atomic mass number. So when we look at the oxygen 16, 17, and 18, and we have the fractional abundance in decimal fraction. You have to do this in decimal fractions. So this is 0.99759, 0.0037, or 0.00204. And then I'll move that over a little bit. Your atomic mass values are 15.9949, 99991, and 17.9992. Basically, it's multiply the two numbers together to get the average. This is the weight contribution over here. Over here, when we multiply those two together, what this boils down to is you're given the fractional abundance in decimal fraction times the isotopic mass. So don't misinterpret that. And of course the fractional abundance or percentage. Multiply those two together and you will obtain the weight contribution of oxygen 16. And then oxygen 17 is calculated the same way, and oxygen 18. Then you add these together, and this is the published atomic mass for the element. And the units are AMU. Atomic mass units, and represent relative mass values relative to, say, carbon-12 as the standard. And there's some variations, but it means 15 to 12 mass ratio, or 15 to 16 mass ratio. And it's 16 times heavier than hydrogen. So that's essentially what it refers to. Now we'll see units show up in different formats later on when we get to calculations, and we'll change them to grams, and represents the mass contained in 1 mole. And so 1 mole of oxygen 16 is the most abundant isotope, is 15.9994 grams per 1 mole. But this is how the numbers on the periodic table are obtained for various elements. Okay, in a problem like this, one little footnote you need is, remember, when you're adding percentages of a mixture, the outcome is 100%. So A plus B gives you 100%. Fractional abundance, though, will give you 1. Fractional abundance of A plus fractional abundance of B in a mixture gives you 1. And so keep that in mind as we go through this setup on this. Now, with that in mind, we have a fractional abundance that we are trying to determine, and then at the end of the problem we can times 100 once we calculate each one and get the percentages. That is fractional abundance of copper 63 plus the fractional abundance of copper 65 equals 1.0000 if you want to carry it out that far. That makes sense too. It's like a percentage. I got a percent of copper 63 and a percentage of copper 65. If we added those together, assuming those are the only two isotopes, then this should be 100%. But again, if we're working with decimal fractions, the sum of the decimal fractions always gives you 1.000, like that. Now, the next equation that you associate with this is the sum of all the weight contributions. We need a weight contribution of copper 63 and a weight contribution of copper 65. Well, the weight contribution, if you recall, was the fractional abundance times the isotopic weight. And so that would be for copper 63 plus the fractional abundance times the mass of copper 64. And that sum will give you the weight average atomic weight that's published on the periodic table. Okay, so you'll recognize this as two equations and two unknowns. And so you would solve the first equation for either the fractional abundance of copper 63 and then substitute the 1 minus fractional abundance of copper 65 into this second expression right here. So if that's the copper fractional abundance for copper 63, you would have fractional 1 minus fractional abundance of copper 65 placed there, where you're given the mass value up here, and so you can reduce that expression to one unknown and solve for that one, and then come back and use the first expression to solve for the other fractional percentage. You see the strategy in this, everybody? Okay, I'm going to give you the answer and let y'all do that so we can move on to the ions. And if you struggle with it, send me a note or we'll go through it next time. But I need you to invest a little time in this. The answer to this is the percent of copper 63 that the answer book gives is 69.17%, and the percent of copper 65 is 30.83%. See if you can solve the first one for either or of the fractional abundance, and substitute in the second equation, solve for the remaining unknown. And then once you get the remaining unknown, then you can put it back in the first equation, get the second percentage of fractional abundance. By definition, ions are charged particles and result from gain or loss of electrons. And I'm going to add one other thing to this. It's very important. It kind of shows you the natural order of the universe. By path of least resistance. Is the key in understanding what I'm about to share with you. Now we know that the atomic structure is, of course, a nuclear structure followed by the electronic cloud. And 1, 2, 3, 4, 5, 6, 7. The inner rings are known as the core structure, and the outer shell is known as the valence. It is to and from the valence shell that variations in electronic numbers occur. That is, all chemistry occurs at the valence level. That's level on there. So as we go through this, we're talking about gain and loss of electrons from or to the outer shell, and we will pretty much ignore the other shells in there. Now, as we get started, where is the outer shell in the periodic sequence in the series? Okay, when you look at your periodic table, notice that there are 7 rows. This 2 at the bottom typically inserts, see right in here, see it jumps from 57 to 72 and 89 to 104. So these 2 rows actually go in there, but it's extracted for, I don't know, convenience. Anyway, if you number these 1, 2, 3, 4, 5, 6, 7 rows, they're called periods or series. What the row says about, and listen to me, the row says about an atom in a given row is that it has that many rings around it, energy level. So hydrogen and helium only have 1 ring around them, or 1 energy level. And all the elements in row 2 have 2 rings around them. And row 3 has 3 rings, and 4, 5, 6, 7 rings, and so forth. Where the valence level is the outer shell, and you will recognize that as the highest principal quantum number later on. But the hydrogen and helium will gain and lose electrons, if they gain or lose them, from n equal 1. For elements in row 2, the gain and loss of electrons will occur at the ring 2, or second energy level. And the first energy level will be stable, as it's said, and will not gain or lose. And third energy level will be the gain or loss in the third row. Rings 1 and 2 do not gain or lose electrons. So that's the fundamental that you need for to get started on this. Now, let's go back here and pick up, oh, I know what I wanted to do. In the elements, sometimes I have 2 or 3 directions I want to go, but let's start. Let me give you some terminology here. Starting with the boron and aluminum right here, and then come over to germanium. Let's see. Or is it yellow? I'll come through here like that and over, and I'll just do it like this because there's a lot of variations in this. Yeah. right here. This block of elements looks like a staircase right in here. Are referred to generally as the metalloids. They have characteristics of metals and non-metals depending on the compound that they are contained in. However, on the left side of this staircase-looking division is what we refer to as the metals. Except for hydrogen, and it is in the first row because it has one outer shell electron, but technically it is a non-metal. But so your metals really start right in here. The other side of this staircase are the non-metals. Carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, silicon, selenium, bromide, iodide. Those are the primary non-metallic materials. Now, when we talk about gains and losses of electrons, we always talk about it in terms of what we call the octet rule. Elements tend to gain or lose electrons to achieve a noble gas configuration. Well, this last column in here is called the noble gas column. Noble gas elements. Helium, neon, argon, krypton, xenon, and radon. Well, all of them have 8 outer shell electrons except helium. Of course, it has 2. So it's gain or lose to achieve a duet, or for everybody else, is gain or lose electrons to be an octet. And that's called the octet rule. Configuration by path of least resistance. When we look at the periodic table, elements, we're going to talk about this group right in here is transitions, and we're not going to talk about them right now. They are metals, but I will, and so are these down here called intertransitions. These are the transitions, intertransitions. What we're going to work with is a column 1, column 2, 3, 4, 5, 6, 7, and 8. Like that for right now. And so what I'm going to show you is when we talk about hydrogen, it has 1 outer shell electron, it has 1 ring, 1 outer shell, and then helium has 2 outer shell electrons. And we come down here to lithium, it has ring 1, but it starts with ring 2, and ring 2 has 1 electron, and ring 2 has 2 electrons. And when you get to beryllium, ring 2 has 3 electrons. When you get to boron, 4, 5, 6, 7, and 8. Okay? And so forth, and it repeats, and the third ring is 1 to 8 again through what we call the main group elements. That is 1, 2, 3, 4, 5, 6, 7, 8, or the 8 groups as you see at the top of your chart. Now, if we go by the octet rule, elements tend to gain or lose electrons to achieve a noble gas configuration. Everybody gains to that, gains or loses to achieve that whatever the noble gas configuration is. If we start with lithium, for example, its atomic electronic structure would be 2 electrons in n equal 1 and 1 electron in n equal 2. So what would be the preferred process here? And remember the phrase path of least resistance. Okay? You can either do one of two things. You can gain 8 electrons to achieve a neon configuration, or lose 1 electron, and that will give you a helium configuration. The path of least resistance would certainly be lose 1 electron. To say it would gain 8 electrons onto this structure, remember that lithium only has 3 protons in there. And so trying to add 8 electrons onto the positive charge, or the attractive charge given by 3 protons, that wouldn't be strong enough to hold them to begin with. So it would be much easier to lose 1 electron than to gain 8 or 7 electrons. I should have said 7 electrons because I already got 1. I'm sorry. If we go to lithium beryllium, it too would follow the loss of electrons by path of least resistance. And so in the process, this would go to beryllium and it would remain in that form, and the outer shell, this would lose 2 electrons and go back to the helium configuration, the previous row's configuration. Well, when it does, remember this has 4 protons in there, but now it has lost 2 electrons. So it lost 2 negatives, and so the net charge now on this is +2. So beryllium becomes a +2 ion once it loses its electrons. Up here, I forgot to put it in, but lithium goes to lithium with the helium core and would have a +1 charge on it, and we just write that as lithium plus, or we write beryllium as beryllium +2 or 2 plus, depending on your preference. It doesn't matter to me. And I do need to go through a couple more, a few of these. Boron, to prove my point here, 3 outer shell electrons. Its path of least resistance is gain 5 or lose 3. Well, the odds are better for it to lose 3. And it becomes boron with a helium configuration, and this is listed as a +3 in that configuration. Now you get to carbon, things get a little dicey here. And so you got 1, 2, 3, 4 electrons. Up here where you can see it. So we have 4 valence electrons, and a better valence shell. So it's kind of a break-even deal here. So it's in general, the process of gaining and losing electrons for carbon prefers to gain electrons at this point instead of lose. There are more compounds in the existence that have gained 4 electrons to generate the noble gas configuration than carbons who have lost 4 to get to the noble gas. So this would prefer to gain 4 electrons and would go to a carbon with 8 electrons, and that would of course be the neon configuration and would be represented as carbon 4 minus, if you like that notation. Then you go, just to prove a point, I'm not going to go through all the elements on the chart. Nitrogen has 5 electrons in the valence, so the tendency is to gain to the noble gas configuration, which is you need to gain 3 electrons. That means it will have 3 more electrons than protons in the nucleus. Now keep in mind, you can't lose or gain protons. That's not possible because you change the element. Because nitrogen has 7 protons, and if you went to 8, you would have oxygen, or if you lost one, you'd be back to carbon. So we have to stay at 7 positive charges. Well, that means only the negative charges will undergo change. So gaining 3 electrons would of course go to a nitrogen with 2 in the first energy level, now 8, and that would give you a nitrogen with 3 extra charges, negative charges, and we list that as a 3 minus in that case. So oxygen has 2 and 6 and would gain 2 electrons. It would prefer to gain 2. It's got enough positives in the positive charges in the nucleus to hold the extra electrons, and would go to an oxygen with a 2-8 configuration, and that would be oxygen 2 minus. And then finally you would have the fluoride, number 9, it'd be 2 and 7, so this would gain 1 electron and go to fluoride 2 and 8, which would be fluoride -1, and so forth, like that. And then it would repeat in the next row and do the same thing. Now there's some common issues that you need to be aware of in the periodic table as you study it. Now, when you look at the periodic table, there's some common issues that you can apply. First of all, the main group elements 1A, 2A, 3, 4, 5, 6, and 7, 8 refer also in each column the number of outer shell electrons. That is, 1A has 1 outer shell electron, 2A has 2 outer shell electrons, then we have 3, 4, 5, 6, 7, and of course there's your octet. So everybody in the first column has 1 outer shell electron, 2 has 2 outer shell electrons, and then 3 outer shell electrons. Now the generalization, if you want to split them like this, make a little staircase, that goes down straight down like that. One of the common things that you need to look at is the metals versus the non-metals, and we'll throw in everything to the right of the staircase like that. So anything that's in the metal collection, even out to the boron side of it, these tend to lose electrons, and it forms a positive charge, whereas the non-metals all tend to gain electrons and achieve a negative charge. So there's a generalization for the whole group like that, and that loss of electrons also includes the transitions and inner transitions that we'll look at. So if you know how many, looking at the chart, you know how many electrons refer to the outer shell, then you can think in terms of, well, I got 1, I'd prefer to lose 1 instead of gain 7. So there's a generalization that all of these will lose 1 electron. And then everything in column number 2 has a greater tendency to lose 2, and 3, 3. And then 4 is the petition, and even though I go straight down, it petitions to start gaining 4 electrons. So if you lose 1, everybody in this column has a +1 charge on it if it becomes an ion. And so in the one with 2 outer shell electrons, it would prefer to lose 2. So this would be a plus, well, not there obviously, +2 all the way down. And then you would have the +3s would result from gain or loss of electrons like that. Now, if you gain 4, you just go down through here, and the majority of them are in carbon and silicon. And so they would have a surplus of electrons, meaning they have more negative charges than positive charges in the valence structure or the electronic cloud. You can even go down through here, make them all -4 if you wish. Nitrogen collection in here tend to gain 3. So everybody in the group 5 would tend to gain 3 or have a surplus of 3 electrons all the way down. Oxygen grouping would have a -2, 2 all the way down. And the halogens a -1 all the way down. So there's some generalizations here based on the octet rule that you can apply in defining the charge values of individual elements. Now, the metals, these are transitions. In here, and these are inner transitions. Both are transition metals. These both tend to lose electrons. They have 2, 3, in some cases up to 5 valence electrons in the highest energy level that they will lose. But when they do lose them, they will have not an octet. They will not have a true noble gas. They call them pseudo-noble gases. For example, zinc here has 10 outer shell electrons. And when it loses 2 outer shell electrons, it will have 10 left in the remaining shell. We'll show the logic of those elements as we get into deeper into the configuration studies. But at any rate, this should provide you with a starting point in understanding the idea of, well, how do ions form? They simply form by natural process through the path of least resistance. Now, in defining charges on elements, you have 2 possibilities, what we call variable charges and fixed charges. Let me back that up a step here. I should say something else. There are periodic table charges is what I call them. And then there have compound charges. To define the charge or ionic state of an element, you can go to the periodic table and say, well, this by itself would prefer to lose or gain electrons. Just looking at it, like sodium. It prefers to lose an electron, and it'll float around solution as a +1. Sulfur, and by itself, or oxygen by itself, would be a -2, or halogens -1 when they float around by themselves. However, you put it into a compound, their new rules take over, and they may not fit the periodic table. So this is the point I'm trying to get to. Right now, we're talking about charges that come from the periodic table based on gain or loss electrons that I'm showing you right now. I'll give you an example. Sulfate, -2. Well, the oxidation states or charges on the elements in here don't follow the, well, oxygen does. It's a -2. But sulfur doesn't. The sum of the oxidation states must equal -2 in that polyion. So what is the oxidation state of sulfur? If we say given oxidation state of oxygen to be a -2, so that's sulfur -8 equals -2, so sulfur equals 8 -2 or +6. So in this, that's a +6 oxidation state or charge on that element. Well, if you look at the periodic table, that doesn't quite match, okay, because it would, by itself, it would tend to gain 2 electrons. So right now, we're not talking about compounds and compound oxidation states. That will come in the next lecture as we get into writing compounds and formulas and what have you. So don't get confused on this. Stay with what I'm giving you in defining oxidation states from the table right now. And then we'll talk about adding rules to that as we get deeper into the course. So when we talk about block groups of elements, we can divide them into really through 3 main structural groups in the periodic table. The blue regions here are referred to as main group elements. And for the most part follow the octet rule. That's one of the common denominators for all of the main group elements. Or the duet rule when it comes to hydrogen, gain or loss of 1 electron. The pink area in here, as mentioned a couple of times, are the set of transitions metals. Now they're characterized, of course, as have metal characteristics, but they all tend to lose electrons and achieve a positive charge. Might as well emphasize that. If it's a positive charge, we're talking about ions that are called cations. And negative charges we call anions. The cation is easy to remember, and there's only one other. It has the only plus in the middle of it, the T. So transition metals will lose and become cations, all of them. And same way with inner transitions. These form cations. Now, when you work with the metalloids, if you start with boron and just staircase down like this, and just go, now, don't block off the last one down here, but those elements that touch that line here are referred to as the metalloids. That touch that. So you have questions on the exam. Which of the following in this list is a metalloid? And you look for the one that touches that staircase. Long and the short of that. Now we have group names. Like here's group 1, group 2. Group 7 and Group 8 are the only ones in the periodic table as far as columns, families, groups, however you want to count is fine. There are only 4 formal names that are associated, and that's Group 1, 2, 7, and 8. Groups 3, 4, 5, 6 do not have formal names. The reason is the characteristics of the elements transition from non-metallic character to metal character. So not all of them have essentially the same behavior in the chemical process. So you have Group 1A. Now these all come out of the main group elements. There are groups like the precious metal groups in the transition, like silver, copper, silver, and gold, for example, are called the precious metal groups in the transitions. But our interest is in the main group elements. This is called alkali metals. Group, I'll name them all first. The Group 2 has 2 words in it, alkali earth metals. I just put plural. Then you jump to Group 7, very important, 7A, called the halogens. And then, of course, you have the Group 8A, which is the noble gases. The other that do not have formal names are referred to as the carbon group or the nitrogen, but it's not a formally accepted in the community in a published rule book. Now, of course, the alkali metals, they all have one outer shell electron and typically go to a +1 oxidation state, and alkali earth typically go to a +2 oxidation state. And they're called alkalis because they react with water and form base alkaline basic systems. Halogens are Group 7 and tend to gain just 1 electron. They have 7 outer shell electrons. And so all of them have a -1 charge, and of course the net charge on their noble gas is 0 because it's balanced. Okay. Now, I mentioned that charges are divided into 2 types of charges that show up on elements, especially when we'll be talking about compounds next class. And in that, they have what they call variable charged elements and fixed charged elements. So variable versus fixed charge elements. So what I'm going to do is I'm going to give you the fixed charge and everything else is variable charge. Well, you can determine what the variable charge is from the formula or the name, and we will cover next time. But you have a set here that you need to know in order to work with compounds in terms of what kind of oxidation states they have within the compound. So the set starts really with groups 1 and 2 and 7, and all of these have +1, as I've shown you earlier. Group 1A and Group 2A always have the same oxidation states. Group 2, of course, has a +2 charge on their elements as you go through, and the halogens are always -1. Fluoride, chloride, bromine, iodine, acetylene, or whatever the heck that thing is. Big. Okay. Now, those are easy to find. Okay? And of course, noble gases are 0, and that's no big deal. But there are some transitions in here that have fixed charges that you need to be able to identify. And to do that, you need to find two elements in the transitions. One of them is silver, and it's Ag right here. And the other one is tantalum. It's in the same row, but it's on here. Over here. Right there. Now, starting with silver, go to the right and block in 2 blocks, like I'm doing here. Now, this is circumstantial. This is not scientific stuff. It just helps you to remember which ones are fixed charge. So that's what I'm giving you. Just kind of a memory device here. Then go over to 3, like this. Once you find silver, silver is always +1. 1 block +1. 2 blocks +2. 3 blocks +3. So like I say, it's circumstantial, but it's a memory device that students over the years have related to very quickly, provided you can find number 79 on this chart. And start there with 1 block +1, 2 blocks to the right. Those two will be +2s, and then aluminum, gallium, this one would be +3s. Now over here, it's a little bit backwards to here. This one will be a +5 oxidation state, but you go over here to these two, and it'll be +4. It's not that difficult to remember. I'll show you another trick. And then you take these 3 and write them as +3s. These are always the same oxidation states. If you count them from left to right, it's 1, 2, 3, 4, 5. So it's pretty easy to, in my humble opinion, to identify the fixed charge elements. And all the others are variable charges when they are placed into compounds. And again, I will show you next time how to extract charge values from either the formula or the nomenclature name of the compound. That's next lecture. We'll focus exclusively on writing compounds and naming compounds and so forth. Your quiz will go up to this point. I think I've covered everything, but I always spend a full session on nomenclature and writing formulas, and I'll have worksheets for you to work with, and you'll have a couple of quizzes because I've covered enough to easily give a couple of quizzes next time. So if y'all got any questions?